All right, so let's get started. So last week we talked about some advanced topics, and as I mentioned, like advanced topics will not be covered in your final. Okay, so this week we're coming back to talk about lecture 4, I/O device and block layers. Actually, we talked about it in the past, like 2 weeks ago. And let me quickly do some recalls because it was far away from now. So this figure is about our Linux, and like the top gray bar here shows the system code interface. And then with using system code, the user program can access the service from operating systems, including process management, memory management, file systems, device, and networking. So before midterm, what we cover is process management and memory management. And after the midterm, we'll talk about the I/O part, so including file systems, block device, and the disk itself. So in this class, we will not cover the device control and networking part because most of this part is a little bit engineering, and we don't have that much of time to cover the topic. So from now to the final, we will talk about from the disk, block layers, and then how file system works and what is virtual file system things. Okay. So before we're going to introduce like what is the storage device, this kind of stuff, I think we need to first give a very brief recap about what is data. So in our current systems, a data would be a sequence of 0 and 1 because now our computer is a binary systems. Okay, so for example, for an image, like it is possible if we only have 0 and 1, then it is a black and white image. So if it is a grayscale image, then probably there are 2 bits or 3 bits. And if it is using a 2 bits grayscale image, then you can see for 1 means like a white color, and 0 means the black color. So for light gray and dark gray, we can use 10 and 01 to represent the image. So you can see like if we are going to represent a more high class images or like a finer image, then we can use higher bits. So you can represent a smoother color. So same as audio. When we're going to store the audio in memory or storage device, actually this is the signal for an audio, and then we will do some sampling. So you can see maybe in this example, we use several blue points to sample the signal. So actually, we will not really store the signal in the storage device. Usually what we store is the sampling point. So in this example, the top pick here, for example, if it is 0111, and this is the things we store in our storage device. So to recover or like to demonstrate or present this audio signal, what we are going to do is to read out all those blue points from like our storage device to memory, and CPU can do the processing on it, and it can recover the audio. So we also talk about like those are the data. So to store those data, like storage device and memory device, the key concept behind them is device consists of material which can switch between 2 states stably. So like when you are using a hard disk drive, it operates on the magnetic fields, for example, the parallel or anti-parallel. And if you're using a solid state drive, the SSD, then it is about the voltage stored in the SSD cell. So if it is a high voltage, maybe it is 0, and if it is a low voltage, maybe it goes for 1. So same as the DRAM, we use a capacitor. If the capacitor is charged, it means 0, and if it is not charged, so it means like if the capacitor is around to be empty, then it represents data bit 1. Okay, so there are a lot of different kind of memory storage device, and they follow very similar idea here. So after talking about the data and storage device, like I do a short summary because you already learned about the process data related things, right? Because you learn about heap, you learn about the stack, those kind of things. And you also heard a lot about there's a file data in our system. For example, when you open your Windows, those files, we call it files, right? So including the media, the multimedia, so like the audio file, the video file, the image files, those are files. And actually process data like heap and image data like, file data like image, they are possible to store in the memory. But actually, in the perspective of Linux, there are different kind of data, right? The heap data, the stack data, those are all process data. And multimedia data, they are called file. So because they are different data, so CPU use different logistic to access those data. For example, for process data, CPU access them by using a load store. So CPU will directly load store the memory to get the process data. And for example, if the data is not in the memory, then there is a patch fault. Okay, so the patch fault is the things you learned already in the prior few lectures. So there are swapping, context switch, those kind of things. And on the other hand, if we are going to, if the CPU is going to access the storage, if the CPU is going to access the file data, so let's say it needs to, the user program needs to use a system code to let the CPU know, hey, we are going to access the file data. So with this system code, CPU can run the operating system, and then operating system will execute things like patch, cache, file system, and context switch. So actually, you can see in the kernel space part, they're using different kernel functions. So for patch fault, like those kind of things, they're using the context switch and patch swapping. And then if the data is already in the memory for process data, CPU can directly get the data by using the load store instructions. But for file data, no. File data should always be accessed by using the operating system. So it should always run through the patch, cache, file system, and context switch. Okay, so this is a difference between accessing the file data and process data from a CPU perspective. Okay, so let me quickly give you a big overview about what we are going to learn in the following few weeks. So from a process perspective, process runs in a user space. And when one process is going to access the data, access a file data in the storage device, first, it needs to communicate with the virtual file system. And then the virtual file system will check the patch cache. And then if the data is not in a patch cache, then we will interact with the mapping layer. So usually mapping layer is file system that you already know, like ext4 or like for Mac OS file system, or like exFAT, those kind of things. They are all file system specific. So after accessing the file system will work with the block IO layer to prepare the request before sending into the storage device. So the last one is the device driver. So using the device driver, the operating system can send the request to the device. Okay, so the gray one is device. Actually, the yellow one and green one, they are all part of the kernel functions. So virtual file system to the block device layers, they are all part of the kernels. Okay, and when it comes to device, like there is a firmware inside the device, this is not the kernel. Okay, firmware is inside the device, so it's the kind of the software inside the device. Okay, so what we are going to focus on in the following 2 weeks, I think 2 or 3 weeks, is the device part. So we will talk about the hard disk drive and solid state drives, and then we will talk about the device driver. And probably your homework, I mean your third hands-ons will be on device driver. Okay, and then the last one will go up to the block IO layer to tell you about like what is the BIO and what is the IO scheduler and how to interact with the storage device things. Okay, so for a storage device, we'll talk about 2 very famous storage devices, hard disk drive and solid state drive. So the key difference is hard disk drive, people are calling them a device with a mechanical component. So what we say mechanical is like you can see here is a motor, and the motor will drive the rewrite head, and the rewrite head will move to read out the data. So most of the components inside the hard disk drive, they're moving, right? The plater will move to the platers will rotate all the time, and then the rewrite head will move across the platers by using the motor to drive it. Okay. And the good things for hard disk drive is it is cheap because like you already know, like in most recently, if you are going to assemble a computer, then using a hard disk drive, even now is still a little bit cheaper than solid state drive, and it is more reliable. What I mean reliable is if you store the data in the hard disk drive, and then if you keep the hard disk drive in a very protected space, then the data will not get lost. Okay. So on the other hand, solid state drive, actually solid state drives, it compresses a lot of chips on it, and there is no moving parts. What I mean moving parts is there is no mechanical things inside solid state drives. All of them, they are about the semiconductor things. So there are all chips on it, and there is controller, there is like memory, those kind of things. They are all semiconductor stuff. So no moving part on it. So the great thing is about because there is no moving heads, there is no moving platers, so it can be super fast. Okay. And the second one is there's no vibration or noise because when you are using a hard disk drive and those kind of platers, it rotates all the time. And when the rewrite head needs to move across the platers, and here the mechanical structure will, there are some noise from them. So this is the reason why hard disk drive is usually noisy. And because there's no moving part, it is lighter and smaller for a solid state drive. And it also supports the random access platers. Okay, but there's also very obvious drawbacks for solid state drive as data stored in solid state drive, there is a lifetime. So data will be will get lost if you store the data in a solid state drive for a super long time. And we will talk about what the reason about this kind of lifetime issue later. So first of all, let's talk about the hard disk drive. So this is a physical organization of a hard disk drive. I think you can find these figures in your the financial books of your operating system textbook. So you can see like image like this is an arm, and for this arm there are several heads, and this head is going to read out the data from the plate. So the data is stored inside is stored on the plate. So on each plate there are several tracks. So this is a concentric track. Okay. So you can see like each plater has two sides, and you can store the data in two sides, the top and then bottom. Okay. And usually there is a tiny distance between the arm, or like you can think about the head and the plate. The reason is for hard disk drive, they are using a magnetic field to read out the data. So it doesn't need to touch, I mean, the head doesn't need to touch the plate. We can use the magnetic sense, the magnetic field to sense the data from the plate. Okay. And all platers are bundled together by a spindle. So the spindle can rotate, and at the same time, all the platers can rotate at the same times. Okay. And the surface of a plater is logically divided into concentric circles called tracks. So this is the things what I mentioned, like this is tracks, and there are several tracks here. Okay. And each track is divided into fixed size sectors. So each sector is usually 512 byte, or there are some other cases they can be 4 kilobyte. Okay. And sectors is the minimum access granularity for hard disk drive. So for hard disk drive, you should at least write at a size of 512 byte. For example, if you send a request to the hard disk drive and you are saying like, hey, I only need to write 200 byte, but hard disk drive will still read out the 512 byte to the cache on the hard disk drive, and then it returns the 200 byte to you. So for the mechanical part, for the physical part, it should read out for 512 byte as a minimum granularity. Okay, so let's talk about like how to rewrite the data from the hard disk drive. So there are three main components for the disk performance. The first one is the seek time, and the second one is the rotation delay, and the third one is the transfer time. So given an example, like this is one head, and then this is a plate, and here is a spindle in the center. So for each kind of block with the numbers, it is called a sector. So this is sector 0, 1, 2, 3, 4, 5, 6, 7. So if, for example, in this case, if the plater now is, sorry, if the head now stops on sector 22, but now we get the request is we are going to read out sector 2. So sector 2 is here. So first of all, there's a thing called seek time. So the time to move the disk arm to the correct track. So if you still remember, from 0, 1, 2, 3 until 7, those head sectors, they share one track. And then the second track is from 8 to 15. And then from 16 to 23 is another track. So now the head is located at the inner track. So we are going to move to the outer track. Okay, so like this. This is called a seek time. So in average, the seek time will be 4.9 milliseconds because we need to move the head. Okay, so actually, when the head is moving, actually this plate is rotating all the time because when you start the hard disk drive, the spindle will rotate all the time. So this is the reason when you power on the hard disk drive, it is quite noisy because the spindle is rotating all the time. So there is another thing, it's called rotation delay, because we cannot make sure when we stick the head from the inner to outer, at the same time we can point to, for example, sector 2, because the plate is rotating all the time. So the worst case is, for example, this is sector 2, and the worst case, for example, if the time like the head moved to the outer track and maybe it is on sector 6, then we need to wait for the half of the track moving. Okay, but I mean, long story short, rotation delay is to rotate the spindle to move the desired sector under the disk head. So in this example, like, because this is disk 2, you can image like when this is rotating all the time, then one day you can get the data from sector 2. Okay. So maybe when you are buying the hard disk drive, you will see there's one performance factor. It is called rotations per minute. So RPM for short. So for example, if there is a 10,000 RPMs and you doing some calculation, you can estimate actually it is about 6 milliseconds per round. Okay, because like rotates per minute is like you can for 1 minute you can rotate like 10,000 like rounds here. Okay, so the third one is the transfer time. So in this scenario, I mean the head is now on the sector 2, but we still need to read out the data, right? So as we say, we will give the circuits. We'll give the currents, and the currents will induce the magnetic fields. And using the magnetic field, we can sense the data from the sectors. And then this is called the time to rewrite data to the surface. Okay, because you need some you need some time to adjust the current, and then you need to sometimes to adjust the magnetic field to read out the data. So there's more details later to let you know how to do this kind of transfer. So there are 3 main steps. So this is the reason why hard disk drive takes longer time to deal with the random access, because when you look back to the rotation delay and seek times, actually it is about to moving the platers and the head all around. So for example, if this is, I mean, if the assets, the following assets, there are all sequential assets. What I mean sequential is, for example, sector 2 followed by sector 3, 4, 5, 6, 7, and 0. Then the head doesn't need to stick to all the places. It just stays here, and then the plate rotate all the time. So we can sequentially read out the sectors from 2 to 0 by this direction. Okay. So, but the thing is like you can image if now there is a thing called random access is you first access sector 2 and then you're going to access sector like 19 and then like 5 and then 0 and 16. So if the access pattern like this kind of things, this is called random because they are all random across the disk plate, and the performance will be super low because you need to stick to a lot of places and you need to wait for a rotation. So the seek time and retention delay will be super time consuming for the random access. Okay. Okay, so next question is, so how to read and write the data from the sector? So we say there is a letters there, and we just move the head to the some place and we can read our data, right? So actually, when you break down the plate, actually like this, for this track, if you break down this track, and you can see something on this. So this is the whole track. And on the track, there are several recording medium. So you can think about this is 1 bit, 1 bit, 1 bit. And because one track is like one sector is 512 byte, and for one track, there are several sectors on it. So this is the recording medium is a minimum like storing cells. Okay, so you can imagine this is a super long tracks, and on the track, there are several sectors. For example, these three, maybe it's one sector, and inside a sector, this is the recording medium. So actually, sector is a logical unit. So this is the reason why now we only have the track here, because track is physical and recording medium is physical layer. Okay, so this one is called read head, and this one is called write head. So write head is way more larger than the read head. Okay, so here are several wires here, and we will explain later. So the very basic concept is to read out data from hard disk drive is to check the direction of the magnetic field. So for example, if it is anti-parallel, it will go for 1, and if it is parallel, then we will go for the 0. I mean the decision there. Okay, but what do I mean for like anti-parallel and parallel? And then what is the comparison between two magnetic field? I mean, there is a direction of magnetic field and they're anti-parallel and parallel. So what does that mean? So when we look at the read head, so actually the read head is using the technical giant magnetoresistance. So because this is a terminology, so in Chinese, it would be like 锯齿组效应. So like these kind of things. And you can image one GMR means one free layer plus one fixed layer. Okay, so fixed layer means the direction of the magnetic field will be always static. So fixed layer, because it is fixed layer, so actually we cannot adjust the magnetic field on the fixed layer. But for free layer, I mean the direction for the free layer, it depends. Okay, so this is the recorded medium. So you can think about for this one, you can be this one, the recorded medium. So when we are going to read the data, and for example, if the recorded medium here is this direction, so this is the N direction, this is the S directions. So this is the magnetic field directions, right? Okay, so because the direction is like this, so when the GMR goes through the recorded medium, and there is this recorded medium, this magnetic field will sense for the free layer. So the free layer will becomes like this kind of directions. Okay. So the direction is the left hand side is N and the right hand side is S, right? Because it goes through the recorded medium, so it will be magnetized. Okay. So in this case, because the fixed layer and the free layer is anti-parallel. Sorry. Because the fixed layer and the recorded medium is parallel, so we say this is code 0. And the reason for 0 is because for this GMR, this is fixed layer is on the fixed layer and the free layer is in the different directions. So the GMR will show high resistance state. So you can image like for this GMR, if you give a if you give a current value on this GMR, and you can follow the Ohm's rule, like you can get beta and IR, like this kind of things. Yep.
所以它这个是在到一个之类的市场，会改变出一个想法。是这样子。
Yep. Okay, so there is another example is if the recording medium now is in another direction, if this is N and this is S. So the same things when this GMR, when this read head goes through this recorded medium, and this free layer will be sensed. So this free layer will shows the magnetic field, like the right hand side is N and the left hand side is S. Okay, and at the same time, because this fixed layer and this free layer, they have the same direction of the magnetic field, so it will show in the low resistance state. So the same things, if you give the voltage, you can get, if you give the same voltage, and then you'll get a higher current from this GMR structure. Okay, so the fixed layer directions and the recorded medium is anti-parallel, so we call it 1. Okay, so this is the principle about how to know the data stored in the recorded medium is in which directions. We can use the GMR when the GMR goes through the recorded medium, and we can give the voltage, and then we can test about the resistance state of the GMR, and we can know it is like 1 or 0. Okay. Okay. So this is for read, and then there is for write. So actually, the write head is quite way more larger than read head, and write head is using different technique to write the electric field on the recorded medium. So write head is using the things called inductive write. So inductive write is about like 电流值效应. So about like if you give the right current from here to here, and according to the right hand rule, you can know there is an electric field. This is N and this is S. So for this is N, this is S, and you will sense the recorded medium. And the reason why right head is so large but read head is so small is because for the magnetic field, if you have a larger this kind of iron, actually you can get a larger magnetic force. So larger magnetic force can adjust the recording mediums. I mean the electric field of the recording medium. So this is the reason why the read head is way larger than the read head. Okay, so give a current inside the right head. The right head will give you a super large magnetic field, and then it will adjust the electric directions on the recorded medium. Okay, so this is the way for how right head works. Okay, and the reason here is, but for example, if you have this kind of write mechanism, and it is possible when you are going to write this recorded medium, and because this right head has a higher, it's larger, so it has a stronger magnetic power. So maybe it will be possible to affect the other recorded mediums, right? But actually, in the hard disk drive, in each tray, there is they will leave for a small gap between each recording medium. So like this, actually, there is a small gap here. So this small gap, it is possible, like with a large enough of a small gap, and this right magnetic power will not drive the neighbor recording medium to change their state. Okay, so they use a distance to avoid this kind of change on other neighbor recording mediums. And what's the distance about this kind of two recording medium, and what is the size of the right head? It really depends on different kind of hard disk drive. So different designs will affect the size of the right head and then the distance between different recording medium here. Okay, so this is how the hard disk drive works on this kind of read head and write head. Okay, question. Okay. Okay.
大小的线圈的多少会决定这条线。
Yep. So larger, you can get stronger magnetic power.
Right.
Okay. So the reason is that for the write, you are going to change the magnetic field for the on the recorded medium, right? So you need larger power to change. You need larger electric. You need larger size of the magnetical power to change the recorded medium. But for read, actually, they are using a different technique called giant magnetical resistance. So it doesn't really need to be too large. A smaller one, you can get a good effect on this kind of resistance change. Yep. So, okay. So this is hard disk drive. And notice like actually the read and write head, the size difference is quite large. So there is advanced evolutions for this hard disk drive. It is called a single magnetic recording drive. And now if you go to the market and if you want to go for larger capacity of the hard disk drive, sometimes you will find this kind of SMR drive. So actually SMR drive is, you can think about, it's an extension from the hard disk drive. And most of the things there are the same. The only difference is how to write the data in the in the track. Okay. So the key concept behind the SMR is because the size difference between the reader and writer. So we say writer is larger than reader, right? So conventionally, if you are going to write the data like these kind of things, and you're going to read the data, but you can find actually the reader is smaller, but the writer is larger. So when you are going to read the data, there is a lot of space they are wasted, right? Because you write a large space, but the things that you only need, like the middle, like 70% or 60% of the area is enough for reading the data. So the rest of them, they are wasted. And then the more you waste, then the capacity will be also wasted. So a better way is, because this is a writer, and then the possible thing is if you slightly move the readers to the edge, and then you write the following tracks on the prior tracks. So for example, like this. If you write the fourth tracks, and then you shingle, you overlap with the third tracks, and in this case, you can store more data. You can increase the capacity, and then you can still make sure data can be read out. The reason is like this. In this case, you can read out data, and then because the read head is quite small, it's quite smaller than write head. So for this part, we will not waste it because you already write another data on it. Okay, so you can like double, or you can increase 1.5 of the capacity of using this kind of hard disk drive. And this is the concept of SMR. Okay, so this is the reason why you can see like there are like 15 terabyte or 20 terabyte of the hard disk drive. And in most cases, they are larger than 10 terabyte. Usually it's because they use a single magnetic recording technology here. And for this technology, it doesn't really need to change too much of hard disk drive, because the thing is, you just need to write the track overlap with the prior tracks, and you just need to slightly adjust the position of the reader. Like originally, conventionally, it would be in the middle of the writer like this, and you just need to move to the side of the writer. Okay, but actually, there are some trade-off for using this SMR. I mean, there are some constraints here. So the constraint is it cannot directly update the data in prior tracks. You should read out, modify, write to new track. The reason is like this. So for example, because you already write to the third tracks, but now you are going to go back to modify the data on the second or the first track. For example, here and here and here and here and here. So if you are using the conventional HDD and you just directly write the new data on it, and we're done, right? But for SMR, you cannot write the data directly on it, because if you directly write track 2, then it will destroy the data stored on track 3, right? Because the data is stored here, and if you write again track 2, then you will destroy the data on track 3. Okay, the same things, if you're going to write track 1, then you will destroy data on like track 2 and track 3. Okay. So to solve this problem, SMR say you should only write in a sequential write constraint. You can never go back to write the prior tracks. So if you are going to update the prior tracks, the thing is, we'll first mark them, I mean, in a controller of the hard disk drive, and then find a current pointer, because maybe track 3 now, there's still, I mean, there are still some free space here, for example. Then you can move all this kind of data you are going to update it to append at the tail of the right pointer. So in this case, you don't really need to write the prior stack, the prior tracks. You can always go for the new tracks here. Okay, but there are some following issues here, because if we mark the data here, it means like those market data, they are invalid data, because they are all new data in the very latest few tracks, right? So one day we still need to trigger the garbage collection to recover all this kind of invalid data from the prior tracks. Okay, so the garbage collection overhead is quite expensive for this kind of SMR drives. Okay, so this is for the like hard disk drive and SMR part. Okay. So for the checkbox, I think I will go through it after the class, and then we'll reply those questions in the next class. Okay. So let's first move on. So the second the second storage device that we are talking about is the solid state drive. So because like from your USB device, from your like SSD, and then from your like notebook, you all use this kind of called NAND flash memory stuff. So today we are going to talk about the NAND flash memory. Okay, so like those kind of device that use NAND flash memory. So actually there is a NAND. So like there is also another get called NOR get. So there's NAND flash. So of course there is a flash called NOR flash. So NOR flash and NAND flash, they are totally different. So NOR flash is another technology of replacing the read-only memory, the ROM memory. So for example, it is widely used for BIOS and firmware, those kind of stuff. Okay, but in this lecture, we'll only talk about the like NAND flash memory here. Okay, so I mean NAND flash memory, usually people know it more about is for the solid state drive. So we'll first talk about solid state drive, the architecture of the solid state drives. So assuming this is a 64 GB SSD, so inside the SSD, usually there is one controller. So the controller you can think about this is a micro CPU, and there are also several DRAM here. And usually the size of DRAM, the capacity of DRAM is usually not too tiny. What I mean is, if you are using like, for example, 1 terabyte of the SSD, the DRAM should be at least in 1 gigabyte. Okay, so like if you have a larger SSD, then the DRAM should be larger. Okay. Then the controller, there are several kind of channels will be connected to the controller. So for one channel, like there is a chips on it. Okay. So on the chip, usually there are several dies. So in this example, there's kind of 4 dies on this chips. Okay. So die is the smallest granularity for sending a request. So what I mean is, if there are 10 requests, and then you can say, okay, there are 10 requests. So let me send, like for this chip, they can serve for 4 requests. And this chip, they can serve for another 4 requests. And this chip, they can serve for 2 requests. So totally, you can serve the 10 requests in parallel. Okay. But for this example, because we only have 16 dice here, so if you are going to serve for more than 16 requests, then the 17, 18, or like 20 requests, they should be pending. They should wait for the request finish in one die. And the next one can be sent into the die for the following operations. Okay. So for one die, actually usually there are 2 planes on one die. And for one plane, there are 1024 blocks on it. Okay, so block is the minimum granularity for doing the erase operation for SSD. Okay, and then inside the block, actually there are several pages. So usually there are 512 pages, but it depends. I mean, different SSD, they have different sizes. Okay. So the patch, usually the size of patch usually is 4 KB or 8 or 16 kilobytes. So usually it's these three options. So patch is the minimum granularity for read and write. So same as disk, like when you are going to read data from hard disk drive, then the smallest size should be 512 byte. Okay, and this is a hardware constraint. So when you are going to read out the data from solid state drives, it should be follow the patch. So if the patch is 4 kilobyte, so the minimum granularity should be to read out 4 kilobyte data at the same time. Okay, so when you look into another aspect is the real circuit, what does it look like? So if this is a block, and inside the block, there are several things like this. So actually, there are two different kind of wire. The horizontal wires called word lines. So this is all word lines. So on the word lines, there are several cells on it. Okay, so for one word line, usually it means one patch. So you can think about like this. For one patch is 4 kilobyte, and if one cell here can only represent 1 bit, then you need 4 KB amount of cells to be chained on this word line. Okay, so there are a ton of cells here, and then use word line to chain them together. Okay, and then there is a vertical line called bit line. So bit line is usually used to read out data, something like that. And then we'll introduce what bit line is for later. Okay, so this is the patch. So inside the patch for this kind of mark, we'll call it memory cell. And then later on, we will talk about how memory cells work. Okay, so before that, actually, let's go back to one thing. Okay, so if we are going to know how large, what is the capacity of this SSD? So like in this example, because each patch is 4 kilobyte, and we say there are 512 patches in one block. So you can calculate back how large is a die. For example, this is the patch block, and then there are 1024 blocks in one plane, and there are 2 planes. So one die will be 32 gigabyte. Okay, and then because there are four dies in one chips, and there are 4 chips here, so 32 times 16, there are 64 gigabyte data here. Okay, so this is the architecture of the SSD. Okay, so as we mentioned, like flash memory cells, these kind of flash memory cells on the same word line, on the same horizontal line, they are belonging to the same flash patch. Okay, so noting like the flash patch, even this is called patch, but there is no relation between the always patch. So there are 2 different ideas. But I mean, the size is usually the same. For example, always patch size is 4 kilobyte, and the NAND flash patch size usually is 4 kilobyte. But it depends. I mean, some SSD they can support like 8 kilobyte or like 16 kilobyte. So it depends. Okay. So let's talk about how to rewrite the data from the NAND flash cell. So data in NAND flash cell is stored in, data in NAND flash chips, they're stored in the cells. And each cell can store 1 bit or more than 1 bit. We'll talk about it later. So when we zoom into the memory cell, I mean, the very simple architecture is look like this kind of things. I mean, there is a P substrate here, and then there are N source and N drain. Above them, there's a things called flow and get and control get. So the key thing is the flow and get. So flow and get, around flow and get, we use the things called dielectric there. So dielectric in Chinese is called 电介质, and you can think about it is kind of electrical accelerator. So you can think about it's a special type of the accelerator, and accelerator is called 绝缘体. Okay, and because there are 2 accelerators here, so you can think about if you store the electron inside this floating gate, okay, inside this floating gate, then the electron cannot go outside from the floating gate, right? Because this is the accelerator. So the electrons will be retained inside this floating gate. Okay, so this is the reason why we say SSD or NAND flash memory, it is kind of the non-volatile memory. Because for this accelerator, if you don't apply electrical field on it, I mean, if you don't give it power, then it will become an accelerator. So for the accelerator, the electrons between the two accelerators, it cannot go outside this structure. So it can capture the electron without using any energy here. Okay. Okay, so like this, if there are electrons inside, then maybe we call it represent bit 0. And there, if there are very few, or if there is no electrons, then we say this is called bit 1. Okay, so for this structure, actually you don't need any electric field or electric power, these kind of things. You just put there, and because you put there, then the dielectric will show the accelerator characteristics. So the electrons will be captured inside here, inside the floating gate. Okay, so the data is always there. Okay. Okay, so this is the very brief concept for how the floating gate shows about 0 or 1. Okay, so if you still remember, like this one is the mark that we use in this here. We say this is a memory cell. Okay, so the same things. This is a memory cell, and this is the floating gate we see. So usually you need to look at like kind of things. So this is the word line. I mean the horizontal one. So the word line is here. I mean the word line will connect a lot of cells together. Okay, and the vertical one is called bit line. So bit line will penetrate through the unsourced and entrance. So this is the bit line. Okay. So if there are electrons inside, then inside there is a higher voltage. Okay. So for higher voltage, if you apply a lower voltage value, actually there is no current to get from the bit line. And this is the reason we say this is called 0. Okay, because we cannot receive the current from the end of this bit line. So we will say, hey, this is bit 0. So if, on the other hand, if there is very few electrons inside, so there are quite few, I mean, the voltage value will be quite low. And if you use the same voltage value, then you can get the current at the bottom of this cell. Okay. But why? I mean, what does it mean for this kind of read voltage, and why if you apply the voltage value like smaller than the voltage inside the floating gate, you cannot get the current. But if you apply the voltage larger than the voltage value inside the floating gate, you can get the value. You can get a current, and we'll explain later. So let's take a 10 and come back later.